In this video, I'm going to teach you about boiling and vapor pressure. When liquids evaporate in an open container, as opposed to a closed container that I talked about in our previous video, gas molecules escape pretty much permanently, never to be reclaimed by their liquid brethren. This evaporation, or boiling, continues until the liquid is completely converted to a gas. Evaporation, or boiling, occurs when the pressure exerted by the liquid molecules on the atmosphere equals the pressure exerted by the atmosphere down on the liquid molecules. You can see that pictorially shown in this figure, which I drew myself. As it turns out, liquid molecules actually do exert a pressure up toward the atmosphere, as depicted by this cute little arrow. This pressure is called vapor pressure, by the way. The atmosphere similarly has a pressure called atmospheric pressure, which pushes down on the liquid molecules. As it turns out, when those two pressures are equal, that's when boiling occurs. You can imagine then that if you had the ability to lower or decrease the pressure of the atmosphere down on a liquid by, say, vacuum sucking all of the gas molecules above a liquid in a sealed container, you could decrease that liquid's boiling point. That's shown in this cute little teaching video to which I've posted a link, and I highly recommend you watch because it's frankly kind of cool. Figure 11.25, shown here, shows us that liquids have different boiling temperatures at different pressures. Once again, if I increase the pressure of the atmosphere down on a liquid, it's going to make it harder for that liquid to escape and convert into a gas and hence boil. If I decrease the atmospheric pressure on the liquid, it makes it much easier for those liquid molecules to escape and convert to gas molecules and therefore boil. This figure shows vapor pressure against boiling temperature. For instance, the normal boiling temperature of diethyl ether at 760 torr, which is the same thing as 1 atmosphere of pressure, is 34.6 degrees. However, if you decrease the pressure, so you imagine decreasing the atmospheric pressure on that ether, what do you notice about the curve? The curve goes down, which means that diethyl ether's boiling temperature decreases. We can see something similar for water. At 1 atmosphere pressure, water boils at 100 degrees Celsius. At close to half that, around 400 torr, it looks like the boiling temperature of water goes down to around 80 degrees Celsius, give or take a little bit. Which begs the question, using this figure, estimate the boiling point of diethyl ether under an external pressure of 610 torr. I'm not going to answer this for you, but we'll invite you to do it on your own. Separately, using this vapor pressure curve here, estimate the boiling point of ethanol at an external pressure of 200 torr. Estimate the external pressure at which ethanol will boil at 60 degrees Celsius. Estimate the boiling point of diethyl ether at 400 torr. And separately, estimate the external pressure at which diethyl ether will boil at 40 degrees Celsius. Once again, I'm not going to do this problem for you. We'll invite you to peruse this figure and see if you can determine how to do it on your own. Speaking of vapor pressure, I'm now going to talk to you about vapor pressure. Vapor pressure, the pressure of a vapor. As I intimated earlier, the pressure exerted by a liquid on the atmosphere above it is called its vapor pressure. Generally, molecules with weaker intermolecular forces, that is, molecules that don't stick together as much, they're going to be able to evaporate much more easily, and therefore they will have higher vapor pressures. That is, they push up on the atmosphere much more intensely than liquids that want to stick together by having stronger intermolecular forces. Therefore, molecules that have weak intermolecular forces have higher vapor pressures and lower boiling points. It takes less heat to get them to separate out and escape. Let me write that here for you to see. Weaker intermolecular forces equal usually higher vapor pressure and lower boiling point. So now I ask you, why do you think this is? Now if you don't know, I want you to think about it. I'll post a link here to a separate video that you can watch to review the connection between intermolecular forces and boiling. One more vocab word. Liquids that boil easily are said to be volatile. So please remember that word, because I'm going to ask you a question now about it. True or false? Carbon tetrabromide is more volatile than carbon tetrachloride. Separately, carbon tetrabromide has a higher boiling point than carbon tetrachloride. Carbon tetrabromide has weaker intermolecular forces than carbon tetrachloride, and carbon tetrabromide has a higher vapor pressure at the same temperature than carbon tetrachloride. At this point, I invite you to pause the video and attempt to do them on your own. You can then hit play, and we'll talk through a couple of these together. That takes us to the end of this video. Please watch the next one, in which I'll talk about phase diagrams and liquid crystals. Until then, have an enjoyable rest of your day.